All right, it is 7 o'clock. I'm going to get started. The mic, the wireless mic is out of battery, so I cannot use it today. I kept telling them use rechargeables and just keep two being charged and two in the device itself, so you always have something that's ready to go. They never listened and think that the chargers are too expensive in a classroom like this. They're worried that somebody might steal the charger and the rechargeable batteries. So, so I'm going to use just my voice today, which is not really loud, but hopefully loud enough. Okay. All right. So what we'll do today is to finish up the conversion thing, and from discussing this with various students, I think I have a better way to explain it now. Okay. But I don't have it in my notes yet because it was out of the office hour discussion, so I don't have time to actually type anything. So I'm going to do it on the whiteboard, which means you guys will probably have to take notes today, or have your or have your phone ready to take a picture of the whiteboard. Either way, okay. All right. So I'm going to start with the scientific notation. Okay. So in base 10 scientific notation, you can still break all the numbers into a few components. Okay, so we'll start with a concrete example. So minus, negative, the whole number itself is negative 2.78 e and minus 78. Okay, you can type this number into a scientific calculator. It represents a particular value, right? Is that okay? I'm hoping everybody is comfortable with scientific notation because otherwise we're in big trouble. Okay? All right, so we know what this means. So when you break this up, okay, I want you to break it up so that it is represented as -1, the sign itself, all by itself is one thing, times, and then we have the mantissa. In this case, the mantissa is 2.78. But since I only want you guys to use integer arithmetics, which means you cannot use float or double within your own subroutine. So that means, oh, how do I represent 2.78? Well, how about 278 divided by 100? We can do this, right? Okay, so you have to represent 278 as the numerator by itself, and then represent 100 individually as the denominator by itself. You don't really have to represent the 100 as a denominator because you can just adjust the exponent accordingly. Is that okay? Does it make sense? But in this example, I'm just using it this way first, okay? And then times 10 to the power of negative 78. Is that okay? Does everybody see how this number here in scientific notation is now broken up into 3 components: the sign, the mantissa, which by itself is a fraction, and also 10 to the power of negative 78. Yes?
And then the second, that's going to be adjusted for the decimal.
Yes. So in this case, if I really want to be lazy, I can now get rid of the denominator because that is guaranteed to be a power of 10, right? So we can say, oh, division by 100 is really 10 to the power of negative 2. Why don't I just represent the mantissa as just an integer, right? But now I adjust my exponent of 10 to negative 80 in this case. So I absorb the division by 100 into the exponent of 10. Is that making any sense? Okay, cool. All right. So now the question is, this number, this representation, has one problem because it is based on the exponent of 10. As a double precision floating point number, we want the exponent to be an exponent of 2. So how do we go from here to this? Okay, so what we want is some kind of sign, which is easy, times some kind of mantissa in base 2, times 2 to the power of some kind of exponent. So I'm using a subscript of 2 here to indicate these are exponent and mantissa for base 2, not iteration 2. Are we still doing okay so far with this? So we need this conversion, but we cannot do this conversion in one single swoop. We have to do it like one step at a time. Is that okay? All right. Okay. So now we take this number. Okay, we'll rewrite it on this side. Okay, so the -1, is easy to kind of keep it on the side because that's really just the sign of the number. It doesn't really do any type of, the conversion doesn't impact the sign at all. We might want to do something about 278 because in order to convert it into this form, we basically, in each step, what we are doing is we have the same sign, no big deal. We have some kind of mantissa, but the mantissa is in transition. Okay, so I'm not going to put a subscript of 2 or 10 into it because it is in transition. But then we have some kind of power of 10 that we are still dealing with. Okay, so this is E with a subscript of 10, and then we have some subscript of some power of 2 that we are transitioning as well. But these are all in flux. We're changing, in this process. Is that okay? You can look at the original number as something that has a power of 2 already. It's just that it is a 0. Okay? Doesn't hurt anything, right? Anything to the power of 0 is 1, and you can always multiply that to any number, any value. So you can always attach it to here too. Is that okay? All right. So now that we understand that we're dealing with a value in this representation, we are trying to move all the non-zero exponent of 10 to become exponent of 2. That's what we're trying to do. We're trying to make this E subscript 10 into a 0, and an E subscript 2 would be some useful value. Is that making any sense? Sort of? Okay? All right. So when your mantissa is 279 and your exponent of 10 is -80, that involves a lot of division by 10. Or multiplication by 10 in this case, because we're trying to turn this into a 0. How do you turn a 10 to the power of -80 into 10 to the power of 0? You multiply 10, you multiply 10, you multiply 10, and eventually, after multiplying 10 80 times, then this -80 as an exponent of 10 is going to go away. Making any sense? Okay. So let's go ahead and do this as one step. So what you want to do is to say, okay, this is still 278, and what we are trying to do is to get rid of the non-zero exponent of 10. So we say, can we get rid of 1 and turn this into 79 over here? The question is, what do we need to do with this part here, and what do we need to do with this part here? Is that making any sense? Sort of? Okay. So we'll go ahead and just do this over here like that, and then we'll say, we want to do a division by 10 like that. We want to do a multiplication by 10. See? Okay, is that okay? So does everybody see how I changed the power of 10 or the exponent of 10 from -80 to -78? But I compensate for that by multiplying the 10 to the mantissa. Yep.
What's the purpose of doing that? Of taking that 10 out? I mean, I understand how you got that, but just.
Oh, because we want this to eventually become a 0.
Yeah.
That's what we want to do.
So we have to multiply by 10 80 times then to.
But then you have a problem eventually.
Yeah.
What is the problem?
You reached the limit of the 64-bit integer.
Exactly. You only have 53 bits officially as the mantissa in base 2, which means if you want to represent values precisely, you can only precisely represent up to 2 to the power of 53, or just 1 less than that. Okay, any value that is greater than that as an integer can no longer be represented exactly. Yes, question?
So for the exponent, so your example, it says 80 to the power of 80, but in your previous requirements, I thought it was 0 through 9.
That's your homework.
Oh, okay.
This is in general.
Oh, okay.
So I want to teach you the general case because the homework is just a way for you to practice, to get some hands-on experience. But this is the general way to do it. Okay. Now whether it is applicable to your homework or not, I'll leave it up to you to decide, right? But I'm going to explain this just in case you need to use something like that. right? Okay, so we can keep doing this, okay? So the next one is 100, or 10 times 10 times 278 times 10 to the power of negative 78, and we still do not need any adjustment for, in the exponent of 2. Is that making any sense? I'm just moving the exponent, of 10 into actual multiplication. But at some point, I am going to run out of bits, because this number eventually will no longer be representable as a base 2 number only using 53 bits. Is that making any sense?
So what's the limitation of that? Is it 53 bits, the limitation for?
We only have 53 bits because the mantissa in double precision floating point number starts with a 1 point. This part is implicit.
Right.
And then we have 52 digits to the right-hand side of the point. In other words, this part here has a total of 52 digits. Is that okay? So the largest value we can represent, it would be 1.111111 all the way up to here, times some kind of power of 2, right?
Yeah.
And we can represent, if we can use 2 to the power of 52 in this case, then we can represent, that integer value exactly. We're not losing anything, right? So that's why, we really only have 53 bits to play with, including the implicit 1 point.
Right.
Is that okay?
Yes.
So we want to keep doing this. We want to keep multiplying by 10 until we run into that limit.
Right.
Once we run into that limit, okay, first of all, how do we know that we are running into that limit? This is an easy one because 2 to the power 53 is a number that you can actually compute. Okay? So how do we set up that constant in your C program so that we can detect, oh, okay, we are running up against that limit? Choice number 1, not a very good choice, but it works. You punch it in your calculator. What is 2 to the power of 53? You copy all those digits from the calculator into your program. It works, but not the best way to do it. What is the other way to do this?
Long minus 1?
No.
Long minus.
Okay, second way, which is slightly better, is to figure out the hexadecimal number that is 1 to the power of 53, and then you use hexadecimal number to kind of convert the whole thing. Because if your largest number that you can represent is 53 ones, okay, that's your largest, number, largest quantity you can represent exactly would be 53 ones. That means, 2 to the power 53 minus 1 is the largest integer value that you can represent. So the question is, how do I get to this value? You look at this and go like, I can divide it by 4. So 53 divided by 4 is what? 12 with a remainder of, no, it's not 12, 13. It's 13 with a remainder of 1. Okay, so it's 13, so that means, with a remainder of 1, which means you have a 1 and then you have 13 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and you say, this is the same thing. Is it 1 or is it 2? I think it's a 2. I think it's a 2 here. Because if we're dealing with 2 to the power 52 minus 1, it'll be a 1 over here. But since we're dealing with 2 to the power 53, it has a 2 over here. Is that okay? But this is not a good way to do it either, because it depends on you counting the zeros. Okay, that's not something that I'm good at. Counting zeros when there are 13 of those, no way. So how do you represent this thing? How about this? You use the left shift operator. You shift 1, 53 times to the left-hand side, and then subtract 1 from it. So that's why bitwise operators are very important for this particular homework assignment. Okay, so once you get to this constant, what do? You keep multiplying the original mantissa by 10. Okay, you can use a loop. Okay, there's no quick and easy way to figure out how many times you can multiply by 10 before you run out. But at some point, you're going to run out, right? So you can say while, I don't know, m times 10 is less than some kind of constant. I'm not going to tell you what constant you use over here. And then over here, you just say m gets multiplied by 10 by, and then assign it back to itself. So this loop will exit when it is just a little, when you multiply one more time, it's going to be exceeding the limit that you can use. Is that making any sense? Right? Is that okay? No? Yes.
So that you use that bitwise operator, the one left shift 53. We can actually write that in our code, and it will interpret it as that value.
Yes.
Okay.
In fact, I can test this and see if these two numbers are exactly the same. Okay, so how do we test it? GDB. Okay, remember Swiss Army knife, MacGyver. So we say print 1 left shifted 53 times, I think. Okay. I can fix that. Unsigned, long. There we go. Okay, how about that? Non-zero. The reason why this one is a 0 is because 1 is interpreted as an int. An int is a 32-bit. So if you shift anything more than 32 times when you only have 32 bits, guess what you get? 0. Okay? Yep. So that makes sense. So now I want to print the other one, which is in hexadecimal, and then 2 followed by 13 zeros, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and it is the same thing. Okay, so I didn't goof up here. Is that okay? So let me just repeat, because I know somebody's going to do this. Do not just copy and paste this number. It's not the best way to do it. Do not copy and paste this number either. It is not the best way to do it. Use the left shift operator to do this. Okay, so the key is to use bitwise operators as much as you can so that you don't have to do all the chore. And because anytime we do anything like that, counting 13 zeros or copying a really long number, a mistake is going to happen, right? Okay. All right. So, but in addition to adjusting the mantissa so that we can keep going, we have to stop at some point. This is one way to stop. What is the other way to stop? There's got to be another condition here to stop. What is the other reason that we might want to stop? What if we run out of power? What if our E10 is already fully adjusted, right? So that means in the loop here, you also have to remember to say, oh, we're going up by 1. So it starts with minus 80, then it goes to minus 79, minus 78, and so on. So if you're lucky, you might run out of things to adjust before you run out of bits to represent the value. Is that making any sense? Okay. So you put an OR here, and then you say, oh, if E10 is already fully adjusted, we can get out. Okay, so this has to be a non-negative version. No. And of course, if you do something like this, it's not going to run even though it seems right, it is wrong. A Python programmer will look at this and go like, that looks right to me. A C programmer will look at this and go like, no. The worst part about this code is it looks right, it compiles, but it doesn't do the right thing. Because in C and C++ and Java and a whole bunch of other languages that are based on C, what is it expecting after a while? A single statement, right? Here's your single statement right there. That is in the loop. What about this guy? It's not in the loop. It is right after the loop.
Yeah.
That's not what we want to do. So you got to combine these into one single block statement, so that that block statement becomes the statement that is associated with the while. Yes?
Comparing to, I know this is the general case, but comparing to your video, so why were you doubling it versus multiplying by 10 here?
What?
In the while loop?
Mm-hmm. because I'm trying to handle this particular case.
So you're doing base 10, not doubling it. Like you were doubling it before.
Let me turn it off. Sorry about that. There we go.
Oh, it's because it's positive.
Well, because we started off with a scientific notation like this,
Yeah.
and we want to know the double precision floating point representation of this using 64 bits.
Yeah.
So we have to convert it. This is our objective, okay? We have this representation. We want to convert it into something like this.
Oh, so you're just trying to move the decimal place right now, right?
We want to make the exponent of 10 into 0, and then adjust the mantissa and the exponent of 2 to accommodate, so that we end up representing the same thing, but it's going to use an exponent of 2 instead of an exponent of 10.
So you're just parsing it, right?
No, we're not parsing. We're done parsing. We are actually converting the exponent and adjusting the mantissa at the
so
same time.
Yeah, just.
Yeah, we're just tweaking it. Yep.
In the while statement, is that m mod 10 or times 10?
Times 10.
In the while statement, like the Boolean.
That's times 2. Because I want to multiply first before I terminate the loop.
And then it's m times equals 10?
It's
in the
inside
while?
m is m times equal to.
Okay, cool.
Right. And I think this is less than or equal to, because it can equal to this particular number. Depending on what is c, it can be equal to, because that's the last number that you can actually represent. All right. Yep.
Problem with that, it's easy to overshoot and end up past 0.
Not in this case. In the other case, yes, but not in this case, because when you multiply 10 to this number, it will still be representable as a 64-bit number. So it's okay to check the bound when you're multiplying by 10, but when you're checking the bound for multiplying by 2, which is the other case, when you have a positive exponent of 10, then you cannot use this technique anymore. But you're correct. There's one case where you cannot do it this way. Correct.
I have an infinite loop, yeah.
Yep, you end up with an infinite loop because nothing can be greater than the largest possible value you can represent using an unsigned integer. Yep. Okay, is that okay? So by doing this, we will end up with a mantissa that is really big, but eventually we'll still have some left over here. Is that okay?
Yeah.
All right. So we'll go ahead and can I erase this part? All right, so we'll just make an assumption here and just say that we'll adjust up to a certain point and then we run out of digits as a 53-bit number. So we can go back to the projector and actually count the number of digits here. Okay, and let's see. I'm not good at counting. 4, 8, 12, 16. So we can have 16 digits. So we run out pretty quickly in this case. So now we can say -1 times 278, and then we can have 16 decimal digits. So we will be dealing with 1, 2, 8, 12, and 16. Okay, there we go. Times 10 to the power of what again?
2. Oh, wait.
No. We started off with -80, and we introduced 13 zeros. So we just adjust 13 to the exponent. So it's 80, negative 80
67?
plus
67?
67 sounds right. Is that okay? Are we changing the value that we are representing? Nope. It's the same value that we have been representing. Okay, very good. And then times 2 to the power of 0. Does anyone have a problem with multiplying with a 2 to the power of 0? It's just 1, right? No big deal. Okay, cool. All right, so the next step we want to do is to say, but we still have some 10s to multiply, but we cannot anymore because now the mantissa is needing more than, if I multiply one more time by 10, the mantissa now needs more than 53 bits to represent, which is a problem because our mantissa is only 53 bits wide. Yep.
Every time you multiply by 10,
Yep.
why can't you just divide by what the two's exponent would be at the same time?
Because if you do a 10 and then you divide it by, let's say 8, because 8 is closer to 10, if you do something like this each time, you lose precision. You lose precision big time. Ideally speaking, we don't want to stop here either because we are using 64-bit unsigned integers to begin with, right? So we can actually go a little bit bigger than this before we are forced to have to deal with it in phase 2. So let's figure out how many more zeros we can deal with. So that number is going to be, okay, so here's the question. What is the largest value? What is the constant, okay, that is representing the largest value you can represent as a 64-bit unsigned integer? Okay, somebody's going to whip out a calculator and say 2 to the power of 64 minus 1. That is correct, but I'm not going to copy that number. Yep.
Is it 0, x, and small f's?
How many f's?
30.
No. 64-bit number, right? 64-bit number, each hexadecimal digit is representing 4 bits. 16 f's, right? I'm not going to count 16 f's. That's silly. Okay, so how did we get that number? How did we get that value? Oh, one left shift of 64 minus 1. That is not going to work either. Because if you have an unsigned 64-bit number and you left shift 64 times, what do you get? You get a 0 because you have just shifted everything out of the integer. That's not going to use that's not useful either. So I'm going to use this trick here. I'm going to say unsigned long 0. Yes, 0 minus 1. That's the value that I want. Why would that work?
It's unsigned and you want the other side of the circle.
Yep, exactly. Because the largest value is also just 1 away from 0, but in the negative direction. That's why it works. Now, this is really important. I'm not introducing this only as a trick to get this done. I'm introducing this because we really need to understand the number wheel. This is the number wheel again. Okay, we are looking at the unsigned values represented on the number wheel, and we are turning it in a negative direction. If you turn it in a negative direction, one slot from 0, it is the largest value. Is that okay? All right. So now your constant becomes that number, and this turns out to be, if you look at it in hexadecimal, we can also count the number of f's. Okay, I'm not going to count, but I'm thinking there are 16 f's here. You can use? Oh, you can use the column number? Yep, you can do that too. But anyway, there are 16 f's. Okay, so there are multiple ways to get to that constant. So can we plug that constant into here so that we will terminate the loop just changing the c? The answer is
Yes.
no. Why not? Well, let's think about it. What is c in this case? This c is actually the largest value you can represent as a 64-bit integer, right? So what can be greater than that?
65.
No. This is a 64-bit number too.
Right.
So nothing can be greater than that. If you specify, u in 64 underscore t, cast a 0 to that minus 1 in place of this c over here, and then on this side you have a 64-bit unsigned integer value, well, congratulations, you have an infinite loop. Because no value can be greater than the greatest value. Is that making any sense?
Sorry.
So how do you detect that you are about to run out of bits? Yep.
So you kind of like look forward one step.
Yep.
You compare the last value to the less than.
Yep, exactly. So you basically say this. You get rid of this and you say, okay, there's no need to actually find the largest value that you can represent as a 64-bit unsigned integer because it doesn't help you in this case. Instead, you ask this question, is m times 10 less than m? Which sounds really silly.
Yeah.
If you present this to a math professor, he or she will kick you out of the classroom just by asking that question. But in a programming class, it makes perfect sense. Because when you wrap around and you run out of digits, m times 10 is going to be a much smaller number, a value, compared to m itself, because you just wrapped around. Yep?
Yeah, I'm still confused why you're multiplying that.
Because we are trying to adjust E10 to 0. Remember, the whole thing reads like this.
I don't know, just because I pretty much watched the entire last lecture, and you were pretty much doing this exact same thing because the iterations depended on the exponent, right? But when you were doing the iterations, you were multiplying that by 2 every time, not 10.
Because in that particular part of the lecture, we're dealing with a positive exponent.
Oh, so it's different, right?
I think so, unless I remember wrong, what we talked about last time.
That might be different.
Yeah, I think point 13, so it was 13 negative power negative 2. So it was also negative now.
Yep.
Yeah, but we were still multiplying.
Because we want the exponent of 10 to go to 0. If it starts with a negative value, we have to keep adding to it, right? But we don't want to add to this one. Instead, we want to multiply it on the other side. Oh, I see what you mean.
You know what I'm talking about? Like, it does not make any sense right now. 'Cause
Okay, I get you. I get you.
Because you're multiplying by 2 every time to iterate up.
No, because the 10 to the power of some kind of negative power is still implicitly dividing by 10. So I still have to divide by 10. Okay, let me. Oh, but it does make sense because we want this to turn into a 0. But every time I subtract 1 from, every time I add 1 to here, I have to divide it over here. Okay.
Because I remember the only time you multiply by 10 is when you have a decimal.
Right, okay, you're right. I did do it in the opposite direction.
So is this right or no?
This is not right.
Oh, okay.
Yep, okay, so you're right about that. But it is useful when you have a large power of 10 over here to begin with, so it works in the opposite direction. I apologize for that. Is that making any sense? No?
So should this?
I mean, it's literally the same thing, you just multiply by 2.
Okay, so change your original problem to this. -1 times 2.78 times 10 to the power of 80. So it's not -80, it's actually 80.
I mean, I still, because the only reason what in your last video, the only reason you multiply by 10 is just to do the decimal for your denominator, right?
Right. Okay,
And
so
after that, you use big.
so scratch what we just talked about and start with this problem instead. Okay, it will connect to that one. Okay, so let's start with this one, and then what we'll do is we'll jump a few steps, to represent the number. But the point is trying to change the 80 to a 0.
Yeah, because in your video, what you did was your exponent was the iterations.
Right. Yep. So this one, it will still use the same approach that we just talked about, except the original problem needs to have a large exponent of 10, not a small exponent of 10. Not a negative exponent. Is that okay? Okay. So we'll first convert this to 278 times 10 to the power of what? We have a multiplication by 100 over here, which means now 2 of those exponents is now taken care of. Does that make any sense? Sort of? Okay. Okay, so let's not skip that step. You can keep this one if you have already written it, but I'm gonna do this part here. 2.78 times 100 times 10 to the power of 80, and then divided by 100. Is that okay? This 100 should cancel out the other 100, right? Except I'm grouping it like this, so that they do not cancel out. So what I end up with here is 2.78 times 100, which is 278. And then on the other side, 10 to the power of 80 divided by 100 is 10 to the power of 78. Is that okay? All right. So now I'm going to jump to this particular step here. So I'm going to count the number of decimal digits that I can use in as a 64-bit unsigned number, which is this number here. So we copy, and then we'll cheat a little bit here and paste. So that's column 1, this is column 20. So we got 20 digits. Minus 1 times 278, and then we can add, that's more, we can only use up to the last one, so we can only have 19 digits because that number is less than 278 followed by a whole bunch of zeros. So we can only have 13 zeros in this case. Okay. No, not making sense? Not 16 because we have 278 to begin with. So we can only have enough zeros, so it becomes the last number starting with 278 times with a whole bunch of zeros in base 10. Yep.
So the only reason you're padding in this case is because you have such a high exponent, right?
Yes. So we'll say, this is 278 with 13 zeros, okay, times 10 to the power of 13. Then we can adjust the other exponent to only have 10 to the power of 65 in this case, right? But then we group these two together. Is that okay? So now it becomes -1 times 278, and then 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times 10 to the power of 65. Is that okay? So this is the best we can do given that we are only using 64-bit integers. Because when we multiply another 10 to this huge mantissa, it will exceed the value that we can represent using 64-bit numbers. Yep.
Don't you have 13 zeros there in power of 67? Don't you have 13 zeros over there?
That one?
Yeah.
Yeah.
Yep.
And power 67 now, power 65. We have.
Yeah, that's because 2.78 is taking care of the 2. So that's why we're restarting the problem. But this is still okay, right? So now we can no longer move any exponent into the mantissa. Because if you multiply this number by 10 one more time, it's going to exceed the value that can be represented as a 64-bit unsigned number. So now we have to adjust make room by division by 2. Is that okay? So the question is, how many times do we have to divide by 2 to make enough room so that we can divide it by 10 again? Yep.
Is our final answer also going to have the mantissa part?
Yes. So we have a mystery mantissa part, which is to the power of some kind of e here. We're trying to determine this e, but it's going to change. So at this point, this e is going to be a 0 because we can still handle everything without an exponent of 2.
Since 10 is a factor of 2 and 5, can you divide by or multiply by 2 each time?
Well, but because the base is in base 10, is in 10, so you still have to divide. You still have to multiply by 10 or divide by 10.
Oh, I
In this case, we're multiplying by 10, but then we're trying to divide by some power of 2 to adjust for that.
yeah.
Is that okay? All right. Okay. So what we'll do is we'll now rewrite that number, and say this is -1. So remember, the value that we are representing has not changed. It's still exactly the same value. Question?
Yeah, so since last week you used a negative number, we multiplied, since you're using a positive number, you're dividing.
Because the objective is to turn this into a 0. If you start with a negative, you multiply by 10. If you start with a negative number, you divide it by 10 so that the exponent goes away. If you start with a positive number, you multiply by 10 to try to get rid of the exponent. But the idea is to turn the exponent of 10 into 0.
But if you divide by 10,
Because if this is negative and you're dividing the mantissa by 10, then you're doing the same thing as making the exponent closer to 0 by the division done to the mantissa.
but if it's integer division, don't you lose?
Yes, but that's why you want to have a whole bunch of binary power first, so that when you do the base 10 division, when you divide it by 10, the margin of error is going to be small. Because you're dealing with a large number, there's something close to 2 to the power 64 divided by 10, so the mod or the remainder of the division becomes the magnitude of your error, which is going to be small.
I'm just letting you continue.
Okay, all right. All right, so the next thing we want to do is to figure out, okay, how much do we have to divide in order to make enough room to, how many times can we divide this number by 2 so that we make enough room to multiply by 10 again without overflowing the number? That is the question. Is that okay? Okay. So let's call this m, okay? So we need a loop in this case, and you say while, and we're trying to figure out how many times do we have to divide this number by 2 so that we make enough room to do that. So we say while m, I'm just trying to structure the loop here. First, okay. So I know division by 2 is going to be useful. So we have to do this first. The ordering is important. Multiply by 10 first does not work. So you have to divide it by 2 first. So divide by 2 times 10. If it is, if we have enough room, about this a little bit. We're trying to make enough room, so I know what is in the body of the loop already. We are doing the m/division by 2, e2 plus, because what we're doing is we're adjusting the exponent of 2. And we're trying to make sure that there's enough room to do another multiplication by 10. So I'm just thinking about the condition to specify here. If we don't have enough room, this number is going to be, yeah.
Don't you have to kind of like iterate through the division and then check if that multiplied by 10 is less?
I'm doing it stepwise. I'm doing one division, check, make another division, check, until it works.
This is the whole thing right here.
Yeah, I'm just going to be doing this until it works. So the question is, what is the condition that makes it work? I know this quantity is important. This quantity is going to be wrapping around if I have not gone through enough iterations. So the question is, what am I comparing this to detect that I am still, I know it has to do with the less than. So it's the same thing as n times 5. Okay, there we go. There we go. So that's the condition. So once again, your math professor will look at this and go, this doesn't make sense, go away, right? Because when do you think, m is already known to be an unsigned number, it's not a negative number, right? Everything is unsigned. So if m is unsigned, it is non-negative. How can 5m be less than m? It's because it wraps around. Okay? Now when this is no longer less than m, that means I have enough space to do it.
Why 5?
Because I have to divide it by 2 and then multiply by 10. Or if you use a 10 here, that works. That works. Okay. Which is that exactly. So, and also you have to take into consideration, whether, well, no, you don't have to deal with this. You don't have to deal with this part yet. Because all I'm doing is to figure out, how many powers of 2 that I need to use to adjust it. I know that there's an outer loop here that is, basically saying, the outer loop is saying while E10 is non-zero, keep doing this. Is that okay? So after this loop, when I get to the exit of this loop, what do I know for sure? M has enough room, right?
Yeah.
M has enough room so that m times 10 is greater than or equal to n. Okay, that's good. So now we can actually do the multiplication by 10. So this code continues here with a multiplication. So m multiplies equals 10 again, and then E10 decrements again. Yep.
I was confused how that m times 5 became m times 10. I don't understand how it goes.
Which one?
The while m times 10, you had it as
This
m times
one?
5. No, right above it.
Yeah.
No, the while statement under while E10, you said while m times 10, but you had it as m
This
times
one?
5. I don't understand why you changed it to 10.
Divided by 2 and then multiplied by 5.
Oh.
But then I mistakenly divided by 2 first because, I really should just test m itself, because when m times 10 is no longer less than m, then I have enough room to do another multiplication by 10. So this is the right condition to exit. Or the negation of this is the right condition to exit. Okay.
So, I don't know if this is possible, but it seems like we're kind of, averages, but can I get just like an overview? Because I know we're trying to convert, convert base 10 to base 2, right?
Mm-hmm.
So, like, I'm just like trying to look at the overview, like, when we get into base 2, and we remove the padding from 278, then what?
But this is a good chunk of your program already.
I mean, you don't have to show me the code, I just want the overview.
The overview is,
Like, so it's like, do the base 2 and then remove the padding.
okay, so I can show you, can I erase this part? Okay. So I'll give you the overview, basically it's just a map of the important points that we want to visit. So what we started off with, what do you want to end with? Okay. Okay. So what you're starting off with is a sine times some kind of mantissa in base 10, right? Times an exponent, it's an exponent of 10, so it's 10 to the power of some exponent. This is what you start off with. Now you may say that your mantissa is a decimal number, it's 1 point something something, 2 point something something, but we can always adjust E10 so that it is. Does that make any sense? So this is what you start off with. We want to end this up, okay? So the end point is basically the same size times another mantissa. This one is a base 2 mantissa, and this time, our exponent is an exponent of 2. This is what we want to end up with. Yep.
So to get it to base 2 mantissa, that's when you're done with the iteration of the.
When you're done with everything, you should end with something like that. Does that make any sense?
Yeah, I just know we're supposed to iterate through the exponent and then
So we have to get rid of all the power, all the exponent of 10, and in place of exponents of 10, we will end up with exponents of 2. Is that okay?
Yeah, I'm just confused about the mantis part.
Not actually doing the, changing the exponent part, not really changing.
Right, but when you adjust the exponent, you also have to adjust the mantissa, because the
Right.
mantissa is specifying the quantity of that particular power of whatever base
That's
you're
the
taking.
conversion. Once you're done with that,
Right.
I think that's what's.
Well, once we get to this form, we can then try to format it to fit into the 64 in a double precision for this one. Yes?
Why can't you have just a single loop where in every step you minus 1 from the 10 exponent, plus 1 to the 2 exponent, and then times 5?
Whoa, but that's not gonna work, right? Because if you subtract 1 from the 10 exponent and add 1 to the 2 component, then you are dividing by 5. The value is trying to change.
Okay, then why can't you divide them? No, even if you
Because
multiply
you want to
by
preserve the same value. You don't want to change the value being represented. These two numbers
but it
equal
would
each
still be
other.
the same value.
No, it won't. It won't, because b times 10 times, or 10 to the power of -1 times 2 to the power of 1, which is what you're suggesting to adjust, right? You take away 1 from the exponent of 10, and you add in 1 to the exponent of 2.
And times 5.
Huh?
And times 5.
N times 5? N times 5, okay? So where is the 5 going to?
And to the mantissa.
Going to the mantissa? But at some point your mantissa is going to run out of space.
I know, but why can't you put that in the loop?
Put that in the
Yeah.
loop, leave it over there.
Yeah.
So instead of multiply by 10, you multiply by 5, and then
Because you're having two loops that do the first the take away from the 10, and then the
Right.
add to the 2. Why can't you have them all in one loop?
because this will work in any base conversion. You can start with a base 7 number and it will still work.
Okay.
But if you simplify it to a 5 first, then it will only work when you're dealing with specific numbers. So I would much rather stay with the original base and the target base. Yep.
You're saying while n times 10 is less than m, but that's false to begin with, so it doesn't enter the while loop. So shouldn't you negate that to begin with? Because m times 10 will only be less than m when it goes over the circle, but the very first time you do it,
Well, if it's false to begin with, it's cool. That's not a problem, right? If this condition is false to begin with, it means we still have room to multiply by 10 in the mantissa. Then we just go ahead and multiply by 10.
so this only works.
This is in the inner loop. This is the inner loop to this one, and this is outside of the inner loop. So the inner loop ends here. This is outside of the inner loop. This is the end of the outer loop. Yep.
So as a follow-up to what you were just saying, so if the condition, if the intermediate function on there, that while m times 10 is less than, if that didn't get met, it would still do mantissa times 10,
Yep.
and then you would
That's
still
correct.
take off 1 from your base 10 exponent.
That is correct, because the bottom line I want to have here, this is the precondition of this line, is I have enough room. And the condition of having enough room is m times 10 is greater than m. That's what I want. If I end up here, I need to have enough space to store the multiplication by 10 back into m. Because if I don't have space to do it, if I already run out of bits, then I better do some shifting and account for that shifting using division by 2. And adjust the power of 2 instead. Is that okay?
Yeah.
All right. So at some point, if you look at this entire loop, E10 will get to 0. Because with the outer loop, eventually we will decrement E10 all the way down to 0, right? So when we exit from this loop, what do we do then? when we as we're going through this loop, what is the intermediate form but as we're going through this loop here? In other words, if you insert, a condition here when we're still potentially in the loop, the value that we are representing is going to be some kind of sign. Okay, the sign is not important. We just kind of take it out of the whole thing, times some kind of mantissa, right? And in here, when we are still in the loop, then we have a non-zero power of 10, and we have a non-zero power of 2. Both of these can be non-zero at the same time. Is that making any sense? This one becomes non-zero because of this. Because we ran out of digits to multiply by 10, and so we have to start to use phase 2 to compensate for that. Okay? This one can be non-zero because we only decrement by 1 in each iteration. So that means it can be non-zero for a long time. It will become 0 when we are done because the condition to stay in the loop is when E10 is non-zero. So when we get out of the loop, we are guaranteed that E10 is taken care of. It is 0. Is that okay? Okay. So when we get out of the loop, then we know the number is minus s times m2. We know it is m2 now because our exponent of 10 is gone altogether. So we know we only have this much left to deal with. Same value, okay? This value is the same as this value over here. Same value. Is that okay? Sort of? Yep.
So, how do you know that the mantis is base value 2 after all that iteration?
How do I know the mantissa?
It's divided by 2 every time.
Wants to know how he knows the mantis is phase 2.
It's M2 because I don't have because 10 because of that. Because E10 at this point is now a 0. So I know I have the mantissa that I need in order to convert this number into a phase 2 floating point number. Because the exponent of 10 is now a 0. E10 started off with, in this case, it started off with 80. Now it is all the way down to 0. Is that okay? Yep.
Does the process between getting our number from base 10 to base 2 change much if we're dealing with a negative exponent at the beginning versus positive, like how you had your example as negative 78 in the beginning of the class versus us doing like a positive 80?
The negative value would go in the opposite direction because in this case what we're doing is we are trying to divide the mantissa by 2 and multiply it by 10 because the objective is to get rid of the exponent of 10 by actually multiplying it. So the objective of the other one is going to be reversed. When you have a negative exponent of 10, then you want to divide by 10 and multiply by 2 so that your mantissa stays same basically.
Okay.
Yep.
This is for a positive exponent.
Yes, this one is actually starting with a positive exponent. Is that okay so far? Okay, so when we get to this point, we still have some more work to do before we can get to double precision floating point number. So the question now is, how big is this number? M2 by itself, okay? Because M2 can be too small, okay? It doesn't fill the entire 53 bits of the mantissa. So in that case, you have to shift it so that it fills up the entire thing, and then you have to adjust the power of 2 to take care of that problem. If it is too long, if this is more than 53 bits long, then you have to shift it in the opposite direction and also adjust E2 in that direction. Is that making any sense? Okay. So you have to find out where it is. Okay. Whether you have to shift it in this direction or shift it in the opposite direction. And the key to use is this number. Is that okay? So you look at M2, and then you look at this number, and we'll call this number, I'll just call it max here. Okay. So you have to compare this M2 to max, and then you say, okay, which do I need to adjust it? That's the question. Is that okay? So if Let me see. If it's greater than max, then you have to adjust it in a certain way. So you say while M2 is greater than max. How do you adjust it? You don't know how much is bigger by magnitude, you just know it's bigger.
Divide by 2.
You have to divide by 2. Okay, very good. So you have to say M2 divide by 2. But before you divide by 2, you want to look at the remainder before the division, because that will help you adjust so that you don't have a bias, right?
Mod by 10. Do you mod by 10?
Not 10 anymore, because this is division by 2.
So mod by 2.
You have to mod, you can mod by 2, or you can do a bitwise division with 1, you can serve the same purpose. So you want to look at the remainder, so you say, int r, use the right type for r, okay, so r is m2 mod 2, or m first m1, either one works. And then you want to do the actual division, so you say m2 division by 2, like that. And then you say, then you have to adjust it based on the remainder, because if the remainder is a 1, you want to round it up. If the remainder is a 0, then you just leave it the way it is. So now it becomes m2 plus equal to r. And on top of that, there's one thing you also have to adjust. Every single time you divide the mantissa by 2, you have to adjust the exponent accordingly. So the question is, how are you adjusting E2? Are you adding 1 to it, or are you subtracting 1 from it? This is already a division, which is subtracting 1, so you have to add 1 to compensate for it. Okay? So, does that make any sense? So this loop will exit when M2 is less than or equal to max. Is that okay?
This is the shift only in case it's greater than max.
Mhm.
Now we'll have another one in case it's smaller than max.
If it's too small, it's not using enough space of the mantissa, right? So we'll adjust it the other way. Okay, so how do we specify the other way? Okay, we say while M2 is less than something, we will do some adjustments. Okay. What is the boundary here? When it's less than what, do we have to do some adjustments? Well, it's something like that. What is the exponent here? We used 53 here already.
2.
Here we go. Because when M2 is less than 1 left shifted 52 times, that means we are not taking up the 53 bits that are supposed to be the mantissa. So what do we do in this loop? M2 is not big enough. How do we make it bigger?
Multiply by 2.
Double it, okay? So we multiply by 2. You can always use a shift operation instead of a multiplication. So left shift by 1 is the same thing as multiply by 2. So it's up to you to decide which one you want to use. Same idea. What else do we have to do? There's no division, there's no remainder, so that part is cool. What else do we have to do?
Adjust exponent.
Adjust the exponent. How do we adjust the exponent? Because we are multiplying by 2 with the mantissa, we have to compensate for that multiplication by 2 by decreasing the exponent of 2. Does that make any sense?
Decreasing.
Decrease. Just like that. Okay. Okay, now the question is, how do we place these two loops? Do we need a conditional statements to point the flow of logic, go to this one or go to this one based on this comparison? Or can I just arrange these two loops exactly the way it is?
Exactly.
You can do that.
Exactly the way it is. One is dealing with the mantissa being too big, right? It will adjust it down. The other one is dealing with the mantissa being too small. They're not going to influence each other. They cannot both be active at the same time. It doesn't make sense. Okay? All right? So when we're all done with this, what is guaranteed to be M in this case? It has to be within a certain range. Because if it's smaller than a certain range, we bring it up. If it's too big, we bring it down. So by the time we are done with these two loops, M has to be between a certain number and another number. Does it make sense? In fact, what do we know about m? What is the lower bound of m? It comes from this condition. How do we get out of this condition here?
It's gotta be greater than 1.
Okay, so 1 left shifted 52 times has to be less than, no, m2 is greater than or equal to that number, right? But it also has to be less than a certain number. So this one is greater than, yeah, greater than is fine. Okay, so we basically saying it is going to be less than or equal to max, right?
Yeah.
But that's great, because now we know m is going to take how many bits to represent? 53 bits. 53 bits, because it's greater than or equal to 1 left shifted 52 times. Because 1 left shifted 52 times is exactly 53 digits. And this is the smallest value when you have 53 bits. This is the largest value when you have 53 bits. So we now have m exactly the same, the width that we want. Is that okay? Now what do we do? Because m is an integer, okay? That point is all the way to your left-hand side, right-hand side, sorry. It's all the way to your right-hand side. But the implicit point is all the way to the left-hand side, just shy of that one implicit one. So we have 52 shift operations that are implicit. So we're not going to do any shift operations anymore. But there are 52 implicit left shifts. The point is, no, excuse me, there are 52 implicit right shifts. So it is as if, okay, it is as if you are doing this, except it is implicit. You don't do this, it's implicit. But you still have to adjust the exponent accordingly. How do we adjust for the exponent when you are dividing, dividing by 2 52 times? Every time we divide, we add to the exponent. So now you have to say e2 plus equal to 52 to adjust for the implicit right shift. Is that okay? We are so close. We are so close. Okay. Can I erase this part? Yep. Go ahead.
Sorry, it's a little bit of a sidebar, but for the maximum constant, is it okay if we use like a global constant to represent
Yeah.
that?
Oh yeah.
Okay.
You can pound define. You can type that number all over again everywhere. It's up to you.
Just wanted to make sure that was okay.
Yep. Okay. So we are almost done. The Batista is in place. The E is almost in place. The sign is in place as well. So what is left to do? Well, the E is a problem because the E here is not in the form that we want. Because in the IEEE floating point number format, okay, we actually have here E is represented as the actual exponent is E minus 1023. And we're trying to figure out this number. We know this number now. The entire thing, we know what it is. We just need to know what is this number. How do we get this number when we know this number already? This is our E2. We just need to figure out E. So E is, okay, so the equation is, we know that E2, which is the actual exponent of 2, is E minus 1023. So how do we solve this equation to figure out what E is? Come on, algebra. E is E2 plus 1023. Does that make any, does it make sense?
Yeah.
Okay, all right. So we do that, okay, so E equals, E2 plus 1023. So now we got almost all the pieces ready, except that we have one bit that we have to drop. Which bit are we talking about? M2 is a 53-bit number. The most significant one of that number does not need to be represented explicitly. So how do we drop that 1 out of the entire thing? No. We forget about 10. At this point, everything is binary. So we don't have 10s anymore. Not subtraction. We only want to get rid of one single bit. Keep the other 52 bits. Just get rid of 1. Okay, shifting is useful, but I'm going to put it on this side. How many bits are we shifting? Where's the bit that I want to get rid of? Is bit 52, right? So I want to shift it 52 times to get to bit 52. How do I get rid of bit 52? This is setting bit 52, unless you do something about it. Yeah? There are two ways to do it. If you already know that M2 has this bit turned on, you can do a exclusive OR. Okay, how do you do exclusive OR? I just did that, but how do you do exclusive OR in C and C++ as a bitwise operation? Remember the gesture that I just did? The caret. That will turn it off if it's already on. Okay? And it's guaranteed to be on because we know the range of M2 is between these two numbers. So it is guaranteed that that bit has to be on. So as a result, if you do an exclusive OR with that bit again, it's going to turn it off. Then you have to store the result back into M2, right? Because that's the whole objective. We want to get rid of that bit. Is that okay? And then what do we do? What about this E here? What do we have to do about it? Right now, it is a number from 0 to 10, 20, 2000, 2047. So what do we do about it? It's an 11-bit number, right? But it doesn't belong to bit 0 to bit 10. It belongs to bit 52 to 62. So how do we move these bits to that position? Left shift. Okay, how many times do we left shift? So that we have 52 zeros padding to the right-hand side. Every time we left shift by 1, that's 1 0 padding. If we need to pad 52 zeros, how do we do it? Shift it 52 times. Okay, very good. So that's another one. What about sign? Sign is either a 0 for a non-negative number or 1 for a negative number, right? So it's a single bit. And where does it need to go? Bit 63, which is the most significant bit, right? So the actual result, which is your X, right? Whoops. It's a very important moment. X is the sign bit. Now this is assuming sign is either a 1 or 0, okay? If sign is either -1 or 1, you have to do some conversion first. So shift it 63 times. That's one component. E has to be shifted 52 times. That's another component. M2 at this point is fully adjusted. It only has 52 bits, which is what we want. And how do we get these things together? You can add them because because of the padding zeros, you can either do this, that works, or if you were true to bitwise operations, you can do that too. That works too. Does not make a difference at this point. I literally just gave you the solution. Well, 1/2 of the solution. What about the other half?
The other way.
The other way of doing things, exactly. So in the other half, you have an E10 that is negative to begin with, right? So if you have an E10 that is negative to begin with, you want to do division by 10 with your mantissa. But you don't want to do any division by 10 when your mantissa is too small, because then you end up with a margin of error that is insanely big. So what you want to do is you keep multiplying m by 2 until you cannot do that anymore. But all the time you have to adjust the exponent of the whole number. And then when it is time to do a division by 10, then you perform the division by 10, you add 1 to E10, and then you keep doing this until you have the same representation down here. So you still end up with the same kind of representation with the other side. The important point being the exponent of 10 will now be a 0 again. Once you have that, the rest of the logic will still be the same. In other words, this part, all the way to here, this part is universal. Doesn't matter what E10 starts off with. If E10 is negative, doesn't matter. If E10 is positive, doesn't matter. You still have to adjust for the mantissa exactly the same. Yep.
Okay, so we started with the number -2.78 and exponent. But at what point we turn it into ones and zeros?
Okay.
Because I mean,
This is already in zeros and ones. This M10 is actually a binary number internally representing the value, but it is representing the quantity of some kind of power of 10. So these are binary already, these are binary numbers, but it is used so that you have a power of, you can have an exponent of 10 to specify the magnitude of the number.
do we have to change 278 into binary and then work with it?
Yes. So the first part of the
once we got a decimal point, we can translate this number into binary and then.
Okay, so you scan the number. Okay, so you have -2.78 E, so let's say 80, okay? So the same number that we're dealing with. So you have to parse the sign first. Now, when you're dealing with a sign, three things can happen. You see a negative, which means the number is negative. You see a positive, which is by default positive to begin with. Or you see something other than a plus or minus, which is a digit, right? So when you see a minus, that's the only time you actually have something to do, because the implicit sign is a positive sign, which means your sign bit is implicitly a 0. But when you see a negative, then it is a 1. But every time you see something that you recognize, you move your pointer forward, so you'll be ready to parse the next thing, right? So when you see the 2, okay, so after you take care of the sign, then you move on to the next stage of parsing, which is parsing the mantissa. When you parse the mantissa, you are guaranteed to have at least one digit to begin with. Before the decimal point, that's part of the homework assignment. Can be 0, right? Yeah. So you basically look at this, and the way I would do it is to keep scanning forward, but when you scan from this point on, you'll be looking for a digit and also looking for a decimal point. Okay? So you basically say E10 is initialized to 0. If I don't see anything, the implicit exponent of 10 is a 0. So you make that assumption. When you start to see a 0, then you say, okay, I have to count the number of digits now. Because the more digit I encounter, then I have to adjust the exponent of 10 accordingly. It's going to move in the negative direction. Is that okay? And then for the rest, you want to convert 2.78 as a string into 278 as a value. So when you encounter a new digit, you multiply the value that you have already parsed by 10 plus the value of the digit itself, and then you move on. I'm not going to show you that code because it's, yeah.
Yeah, it's just like, we're talking here about ones and zeros, but here we started with.
Well, everything is going to be in zeros and ones. The question is, what does it mean? This number is a binary number, but what is the meaning of this value? This value by itself is not the whole story, because it has to be combined by an implicit exponent of 10 to specify the magnitude. What you're converting it into is going to be some kind of integer here, which by itself is also meaningless, because it also has an exponent component to specify the magnitude, except the magnitude in this case is always a power of 2 instead of a power of 10. So all this logic in between is targeting the E10 to try to get it to 0 without losing precision or too much precision. Is that okay? So short of not declaring the variables correctly, I think I gave you a good chunk of one branch of the entire algorithm. The other branch is very much similar, except instead of multiplying by 10, you're multiplying by 2. Instead of dividing by 2, you're multiplying by 2, and so on. It's basically the flip side of this. Is that okay? I mean, with this logic, that boundary that I placed, the special case boundary of the homework assignment really should not apply anymore. This is general, and you can deal with any actual textbook. Yeah. Question?
Yeah, I'm just.
Oh, okay.
Yeah, I do have a question.
Yeah, go ahead.
So, I was trying to connect last week's lecture to this week's lecture.
Okay.
A little different.
Okay, the lecture from last time is just the notation is different. Okay. Come on, wake up. Okay, so the lecture from last class. Okay, let me get to the lecture.
Predominantly looking at the spreadsheet part.
Huh?
The spreadsheet. When you're doing
The spreadsheet part was an attempt to show you what these loops are doing.
Yeah.
Each row of the spreadsheet is representing one iteration.
Yeah.
And should we get out now? Go on and exit or stop? That is the condition.
Well, I mean, you just had, the M and the p-value and the constant value you added, but you didn't do that here. I got it.
Okay, so when you look at the, let me go back to the assignment. And this note here, okay. So the subscript, in this case, the subscript I is really designating which iteration. The subscript I, every time subscript I changes, is representing one iteration of the outer loop. The inner loop is not represented here. I just basically said you find the largest power of 2 so that blah, 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 blah happens.
Yeah.
So the inner loop, which is this part here, is not explicitly represented in the notation of this note here.
So when you do find the largest value, that's when you begin to do that.
Right, so you have two choices. Either you can find the power itself first, and then do your shift operation all in one single loop, or you can do it stepwise like what I'm doing here. But they accomplish exactly the same thing. Is that okay? So in the notes here, I am basically saying, okay, find out what PI is supposed to be, and then perform all the shifting and adjust the exponent all in one single step. But in the loop here, I'm adjusting by 1 each time. So it's the number of times going through the internal loop here that is going to determine what is PI. PI is representing how many times do we have to go through the internal loop.
The total.
The total number of times we're going through the internal loop. Right. Are there any other questions? Yep.
Can we move the deadline to Sunday night for this?
Yeah.
So we can work
That will be
that weekend on that.
Okay. Do you guys want to spoil your weekend?
That makes sense. Now we can just.
Okay.
169.
I suppose it's okay. The whole point is I want you guys to do this and understand, the representation and how to do the conversion. So, Sunday it is, not a problem.
Sunday night.
The best part about Sunday is I don't have any lab time on that day. Yep.
It's gonna be due next Tuesday?
Huh?
What just happened?
Sorry? Sunday.
Okay.
Yep. Yeah, which is a day where I do not have office hours. All right, I'll be in the lab. So for any one of you who want to kind of get started with this, I'll be in the lab to help you out.
Just do 2 and make it happen, right?
What is this? What is this called?
Hold on a second. Let me. Okay, there we go.
What is that called?
Bitwise OR. It's the vertical bar. It's a bitwise OR.
Oh.
So a bitwise OR is really just looking at the individual bits as an OR. So if you imagine you have bits horizontally spread out as individual numbers, then you have so let's say one number has x, y, z, and another number has a, b, c as individual bits. So the bitwise OR operator will just say, okay, what is z or c? So this becomes z or c or bitwise OR. So if at least one is a 1, this bit becomes a 1. So it lines up the individual bits of the numbers, and then it performs the OR operation on those numbers. Yeah, the bitwise operators of C and C++ are one of the most important things for low-level programming.
Yeah, I've never had to use it.
You never had to use them.
Yeah.
If you write drivers or low-level code to interact with hardware
And now I'm
directly,
learning now.
oh yeah, I mean, these are one of the most useful things. Yep.
So to get PI, we need to keep track of how many times you go through the loop.
Right, but you don't have to do it using this construct. It's adjusting automatically. For each iteration, it's adjusting E2 already. So E2 is corresponding to the summation, the total sum. It's automatically adjusting, so you don't need to take the PI separately. Okay.
Can you fill it up really just this class?
Okay. Since I haven't really graded a whole lot, I can't really. But I can check your online activities.
Yeah.
I can do that. Let me turn off the projector first.
Have you not graded the 4-bit borrow?
I only graded like 1 or 2 of the assignments.
Yeah.
I'm falling a little bit behind grading. But as I said, I can check your attendance. At least, online activities and find out. Oops. P-R-A-J. Okay. Kind of spotty.
Yeah.
Okay. But since I don't have an actual grade. Oh, I'm pretty sure you have a grade. It's just.
Yeah, just like some assignments.
Mm-hmm. I'm just gonna say A at this point.
Yeah, because I got an A on the first one, and then the B, like an 87 on the second, on the 4-bit adder.
Okay. All right.
Thank you.
Okay, let me try to get out of the classroom to the lab.